Okay, this is like my fourth time trying to record this video. And even if I totally mess it up at this point, we are sticking with this video because I'm not recording it again. So this video goes with the lesson 2.3.1 in PLTW on material properties, and you are encouraged to use the curriculum online as a resource as we work through this. Now, I'm making a video of the lesson components, so some of the concepts that I think we need to go over, and then we'll release into activities. You may have noticed that you have been put into a team of 1 or 2 other people on teams, and that will be who you're buddied up with for this particular activity. I am trying to change them up, so please don't complain to me about who you've gotten partnered up with. All right, so we're going to start by talking about like what are materials, and the PLTW curriculum has a kind of an interesting blurb on materials engineers and material sciences and what those people would do. Let's kind of go through what is a material and what are some properties of materials. So consider that everything must be made from something. Materials can loosely be defined as the stuff we use to make things. A more precise definition of material includes the qualities that give something its individuality and by which it can be categorized. How a material performs in a specific application depends on its properties, its response to heat, light, and other stimuli, and depends on the structure of the material, beginning with the atoms that the material is made out of. So what we'll do in class at this point is we will stop and brainstorm some properties that materials might have and why they might be of interest to a materials engineer. Properties might include the color, the texture, conductivity, whether or not it conducts electricity, its melting point or its freezing point, and density, which is going to be the focus of this particular lesson. They would be of interest to an engineer because the engineer is trying to make something. Now, you don't want to make an insulating material from something that conducts electricity. So it would do absolutely no good to have a wire that was insulated on something that would let electricity pass through. But you wouldn't want, say, to build, let's say, like the housing unit for a light bulb out of something that has a very low melting point because the heat from the light bulb would melt it. And so a materials engineer needs to know how a particular material is going to respond to the different stimuli and influences around it so that they can choose an appropriate material for what it is they're trying to design. In material science and engineering, structure refers to how the atoms or molecules are arranged together in a material. A solid material exhibits either a crystalline or amorphous arrangement of atoms or molecules, and they kind of give you this illustration in the curriculum of a crystalline solid and an amorphous solid, and then they give you examples of each. So even without a chemistry background where you would study this in a lot more detail, you kind of get a sense of which kinds of solids are crystalline and which kinds are amorphous. So crystalline solids would include ice, salt, quartz, diamond, zinc, and iron. Amorphous solids would include glass, gels, wax, and some plastics. Now, why does structure matter? I thought this was a really interesting illustration of why structure actually matters. So diamond and graphite are both made out of the same element, carbon. So if you were to break them down like into the atoms that comprise them, they are both made out of the same atom, carbon. But the structure, like how those carbon atoms are put together, is different, and they result in totally different kinds of substances. A diamond is transparent and strong. It's one of the hardest materials known, and graphite is gray and it's relatively soft. So you'll notice there that it says that graphite is used in pencils, and you wouldn't want the pencil to be super hard. You need it to be soft enough so that when you write on your paper, that it would transfer over to the paper. Like otherwise, what's the point of having a pencil? And that really comes down to the arrangement or the structure of the carbon atoms, not a difference in the atoms themselves. Now, I think this is interesting. Now, for those of you that have taken chemistry and specifically have taken physics, you do, I'm sure, know the difference between mass and weight because those are really important distinctions, especially in a physics class. But for those of you that haven't had the opportunity to take physics or chemistry yet, you might not know the difference. And the reason for that is because in our everyday usage, we actually use them kind of interchangeably with each other. So mass can be defined as the amount of matter in an object. You could think of it as like the number of atoms. That's not really the definition, but it kind of works to develop a sense of, it's like how much stuff is there in the object. That's its mass. Weight is actually the force of gravity acting on that mass. And so you've got, say, like I have the soda can here. Okay, there's a certain amount of a matter in the soda can. That doesn't change depending on where the soda can is. Like there's still the same amount of matter in it. Now, gravity is also pulling on it. It's pulling it directly down. And it's the reason why when I hold it, I actually have to exert a certain amount of force on it that increases friction between my hands and the can so that the can does not slide out. If I don't grip it tightly enough, gravity will pull it out from my fingers. So you've got to like grip it tightly enough so that there's enough friction to hold it up. And that's all physics. Now, as long as gravity is constant, which is safe to assume that on Earth it is, there might be some slight variations depending on where you are on Earth, but that's a pretty safe assumption for us to make. Then mass and weight are directly proportional. That gets into a math term. Directly proportional means this. As one goes up, the other goes up with it in a constant way. So as the mass increases, so does the force of gravity acting on that mass. And it goes up like in a constant ratio. It also means that when the mass is zero, the weight is zero. So if you don't have any matter, then there's no force acting on it because there's nothing there for it to act on. I hope that's obvious. And so if you were to graph it, if you were to graph the relationship between mass and weight, it would be a line going through the origin, the point 0, 0, because when mass is 0, weight is 0. So 0, 0 through the origin, and it would be a line. Okay, this is why we can often use one in place of the other, and we'll actually like switch out from using mass and weight. However, if you were to go to the moon, where gravity is different, your weight would change while your mass would not. And that's where you really start to see the distinction. You would still have the same amount of matter in you. Okay, like you do not lose molecules just by going to the moon. Like you would take your body. I mean, you'd shed some, but nothing out of the ordinary. But the force of gravity would be different because the moon has less mass itself. And so the gravitational pull on the moon is less than it is on Earth. And so if you were to like kind of go off of planet Earth and go to the International Space Station or something, your mass would still stay the same, but your weight would change because gravity would change. Now, since these two values are often used interchangeably here on Earth, it is important to pay attention to which value is being used in the problem. And just a couple of fun facts here. The metric units for mass and weight are the kilogram is the unit for mass. And in science, we do have something called the MKS system, which stands for meters, kilograms, seconds. And so the default unit for mass is usually the kilogram, although you will occasionally see the gram used. And I don't know if you can see this because at least on mine, there's like a little video of me there. And so the unit for weight in the metric system is something called the Newton, and that is named after Sir Isaac Newton, who is kind of famous for some calculus stuff and for his laws of motion, one of which relates force and mass, or weight and mass, depending on, depending on the problem that you're doing. The English or imperial units for mass and weight, well, we already, actually, I don't know if we mentioned the unit for weight. That's the one that you're going to be familiar with. The English or imperial unit for weight is the pound. And the unit for mass, you might not have ever heard because nobody ever uses it. I won't say nobody ever uses it. It's just not very common, and you probably haven't, is something called the slug. So slugs and pounds. And where I mean, like when I'm talking about how we kind of go back and forth between them, we will often convert between pounds and kilograms as though they were measuring the same thing. And they're actually not measuring the same thing. Pounds is measuring the force of gravity acting on you. Kilograms is measuring the amount of matter that's in you. And usually, again, on Earth, it doesn't matter because the two of them are directly proportional. Now, this particular activity focuses on density. Density is the amount of matter per unit of volume, and it is what's called a material property, meaning it doesn't vary depending on the amount of the substance that you have, because you take the entire amount of mass that you have and you divide it by like the size, I guess, of the object, so that you're getting the amount of material per a specific unit of volume. And so they tried to depict that like a high density cube versus a low density cube. If you look at where they kind of put those atoms in there, I guess that's what those are supposed to be. I guess it's supposed to be atoms. That in a high density cube, the atoms would be like packed really, really close together. And a low density cube, there would be more space between them. Now you're not going to notice it. It's not like with the cube on the right hand side there that you're going to like put your hand through the cube. Like they're not that far apart. Like both of these cubes are going to seem solid to you, but if they're the same size and you picked them up, one of them would feel a lot heavier because it's got a lot more atoms packed into that small amount of space, or I don't know if it's a small amount of space, but that amount of space. Now, this is a question from the curriculum. Is mass a physical property of a material? All matter has mass and volume. However, if we think about a material property as something about the material that is the same, no matter its size or shape, then density is a material property while mass is not. Because density is a ratio, its value for a material will not change regardless of how much material you have. Conversely, since mass changes depending on how much of the material you have, it is not a distinguishing material characteristic. In other words, just knowing you have 25.6 grams of steel or 1.5 pounds of polypropylene does not specifically tell you about the properties of either material. Like it just tells you how much of the material you have, but it doesn't tell you like, does it conduct electricity? Does it like float in water? Like it doesn't tell you anything about them. It just tells you how much you have of them. In contrast, when considering a specific object or a solid model, the mass, weight, volume, shape, and surface area are physical properties of the object that are often part of the design constraints or solution criteria. These physical properties vary with different objects produced from the same material, although the material properties do not change. So when you're specifically designing something, then you are interested in the mass or the weight or the volume, even though those might not be material properties. The reason you might care is like, let's say you're designing a unit for an airplane. Well, you care about the weight of that, because the weight, if you design something that weighs like 2 tons, that might affect like how well the plane can fly. If you're designing it for like a truck or something, like you've got to be able to go over bridges without the bridges falling down. And so you actually do care about the mass when you're doing a design, but the mass is not a physical property of the material itself. Now, we are going to do a little partner up, discuss, and then share. And I kind of alluded to this a moment ago. Assuming that the density of water is approximately 1 gram per milliliter, what can you infer about materials with a higher density and a lower density? And why would an engineer be concerned with comparing a material's density to that of water? So in class, we will stop the lesson here and you will get a chance to discuss that. For the purposes of this video, here's what hopefully you could come up with your partner. Materials that have a higher density than water will tend to sink. Ones with a lower density of water will tend to float. And an engineer would be concerned about that. Of course, it depends on what they're designing, but if you're designing something that is going to be used outside and might be exposed to water, you need to know, is it going to float or is it going to sink? You might need to know if it's going to well, I guess that gets into like freezing point and melting point, but how it would behave if it came into contact with water. So if you were designing something for a boat, yeah, obviously these would be things you'd be concerned about. All right, now when it comes to the activity, you're going to have to measure mass and you're going to have to measure the volume of several unknown substances. So measuring mass, this is typically done with a balance or scale. We have the blue scales, and you guys did use them when you did your disassembly of the toy. Hopefully you know how to use them. Now, be sure to zero the scale first, okay? And then you place the object on the scale. So it's just like you need to zero the calipers, okay? And make sure that when they're completely closed, you are getting a reading of 0 on it. You need to zero the scale and then place the object on the scale and read the value off of the digital display. If the object is round, okay, so if it's something that might roll off, you will need to put it into a container, such as a paper cup. And so you will place a container on the scale and zero it so that it is zeroed with the paper cup on it. Then you will add the object, and that should give you the mass of the object. But because you zeroed it with the paper cup, you don't need to subtract the paper cup because you re-zeroed it. If you don't zero it, then you would measure just the mass of the paper cup and then the mass of the paper cup with the object, and then you would subtract the two to get the mass of the object. Always record your units with your measurements, so make sure you know what the scale is measuring in, and that should go on your chart. How to measure volume. There are two options for measuring the volume of an object. One is to use a volume formula. So you typically study these in geometry, whether in middle school, like when you're doing a geometry unit, or you do study them when you take geometry, the course, although you usually don't get to them till the end. This is good to use if your object has a regular shape, such as a cylinder, prism, or sphere. If it falls into like one of those headings, you could use the volume formula. So formulas can be memorized or they can be looked up, but it's useful to have some of them memorized. So here are some of the common formulas. Formula for a rectangular prism is length times width times height. Pretty much that's a box. If it looks like a box, like a traditional box, okay, length times width times height is actually a pretty efficient way to measure it. A sphere is 4/3 pi r cubed, and r cubed means to raise the r to the third power or multiply it in 3 times for those of you who have not yet studied like cubing things. R is the radius, and the radius is half of the diameter. So if you were, say, measuring the volume of a marble, okay, of some sort, you would probably put the calipers around the outside. That's going to give you a diameter measurement instead of a radius measurement. So you would use the calipers to measure the diameter, and then you have to make sure that you divided it by 2 before you plugged it into the formula. Formula for the volume of a cylinder is pi r squared h, again, where r is the radius of the cylinder, and that's half the diameter, and probably the same thing. You would be measuring the diameter, and then you would have to cut it in half before you plugged it into the formula. Now, I put volume of any prism because while rectangular prisms are the most common, and I think they're common enough that they get their own line, any prism is capital B times H, where B is the area of the base. And that might involve you knowing a couple of other formulas. Now, if you think about the rectangular prism for a second, the base is a rectangle, and the area of a rectangle is length times width. Hence, length times width, the area of the base, times the height. So I don't want you to think that that first formula is something different from the other formula. But if the base was, say, a triangle, you would find the area of the triangle and then multiply it by the height. If you haven't taken geometry yet and you haven't really studied like what prisms are and how you even know which face is the base, first ask your partner if you're partnered with somebody who has taken geometry, because they probably know, and then ask me. So if neither one of you has taken geometry, or you have taken geometry and you don't remember anything about prisms, please ask me. I know, I will tell you. Now, that formula actually also works for the cylinder. A cylinder is like a prism where the base is a circle, and the area of a circle is pi r squared. And so if you look at the volume of the cylinder formula, it's really the area of the base times the height, except the area of the base now is pi r squared, the area of a circle, instead of the area of some other shape. But you would find like the area of a triangle, area of a trapezoid. In geometry class, you'll do stuff like find the volume of a hexagonal prism, where you have to find the area of a hexagon. That's not going to be super common outside of geometry class. Now we get into some Miss Taylor notation here. We have volume sub pointy. Volume of pointy things is 1/3 the big capital B, which is the area of the base times the height. You think, well, what is she going for? Like volume of the pointy things. That would be something like a pyramid or a cone, something that comes to a point. And so like, I don't really commit very many formulas to memory because there's a couple of things here. If it's not pointy, so if it's a prism or a cylinder, then the formula for the volume is the area of the base times the height. If it is pointy, it'll be 1/3 the area of the base times the height. And then a sphere is different. Like the sphere, you just kind of have to know. And there's a few other things out there, but nothing that common. And so you would need to probably know the formula for the area of a rectangle, area of a rectangle, a circle, and a triangle. And if you know those formulas, you're probably good to go with any of your volume formulas. Like, it's about saving brain space. So don't memorize like tons of formulas. Like, memorize a few concepts, and then you don't have to memorize a lot of formulas. Now, there's other ways to measure the volume. So we have option 2, which is to measure water displacement. Now, this is good for irregularly shaped objects that you cannot measure easily with the calipers or a ruler. So there would be like say a chess piece, like that is shaped like something weird, and you're not going to get like a good measurement on that. Or it has too many parts to measure efficiently. So maybe it is made up of a bunch of rectangular prisms, but there's just so many of them that it would be inefficient for you to try to get all of the measurements to calculate the volume of the formula. So here's the process. You place enough water in a graduated cylinder to completely submerge the object. So if you're not sure what a graduated cylinder is, these are used in chemistry and physics like quite a bit, but they're usually like on a little bit of a stand, like so. And they're a cylinder. That'll surprise you. Okay, or like a cylinder. And graduated just means that there are little measurements on the side. So there's some vocab for you. So it'll have some measurements on the side. So you're going to dump enough water into the graduated cylinder that it should completely like submerge, like the object that you're measuring the volume of should be able to be completely submerged in it. Then you're going to measure the water level, and you always measure from the bottom of the meniscus. So you say, what is the meniscus? The meniscus is this. If you've never looked really closely, you put like a bunch of water. Water has this like property, and it's been a million years since I've taken a physical science or chemistry class, but it's got this like cohesive property where like the water molecules like want to stick to the sides of the graduated cylinder. And so what the water molecules will do at the edges is it'll kind of like climb up the cylinder a little bit, and it'll create this what's called a meniscus. It's like a curve or an arc in the water. And you might not have noticed it before. You notice it more in very narrow graduated cylinders as opposed to the broad ones. And the ones we have are pretty wide. So it's not going to be a pronounced meniscus. But you always measure from the bottom of the meniscus. So you look at where it's curved, and then you measure the bottom. That's where you get your line from. Then you place the object in the water so that it sinks to the bottom. And then you measure the new water level. So I think you guys can probably figure out how this is like working. You put your object, your like little irregularly shaped object, okay, into your water, and the water level is going to go up. And then you would measure the new water level. That's like really messy there, but you guys get the idea. You measure the water level at the bottom of the meniscus, and then you subtract the two measurements. The volume of the water displaced is equal to the volume of the object. So the object will displace an amount of water equal to its own volume. Now, if the object is too large for a graduated cylinder, or it floats in water, then you would have to combine methods. So you might have to do a little bit of like using the formula and also submerging in water. So last year we actually tackled this in IED, and students were like, well, you could like take like a wooden rod that you would push the object down, but then you would have to find like the volume of the rod that was submerged, and you'd have to subtract that, or use your ingenuity to figure out a new method. So what if it was too big to submerge in a graduated cylinder? How could you do it? That's why we're engineers. Now, to calculate the density, once you know the mass and the volume of the object, you can calculate the density using the formula density is equal to mass divided by volume. PLTW will throw at you like weight density and mass density, and just all that means is like mass density, you're using the mass, and weight density means you're using a weight. Don't overthink that. The units for density will come directly from the calculations. So if the units in the numerator are grams and the units in the denominator are cubic centimeters or centimeters cubed, okay, so you've got grams in the numerator and you have cubic centimeters in the denominator, like so, then the units for density will be grams per cubic centimeter. Literally coming directly out of the placement of the units in the calculation. So it's not voodoo and it's not magic. The units for density come from the math, and that is actually true for any units in physics or chemistry that are what are called derived units. So like a Newton comes, what is a Newton? It is kilograms meters per second squared. So you can always like break them down, and you can actually use that when you're doing unit conversions to convert between like say pounds and kilograms, because the units kind of act like a variable. Now, partner activity. We will have, I ordered them today, but we will have, by the time we're ready to do this, 18 sample materials. You and your partner will choose 4 of them, and you will try to identify them by calculating the density. So you're going to calculate the density and then look up on a density table densities of different substances, and you're going to try to figure out what your material is. There will be 6 groups, so you will not have all 4 materials at once. So you're going to take like your first sample, like from the group of 18, you're going to write down which sample that is. You're going to find its density, and then you're going to put that back, and you're going to take another sample, and you're going to put yours back so that like another group can use it. And that way, like there should really only be 4 of the cylinders or 6 of the cylinders out at once. And then as people bring them back, you can take one. Even though you are working together. So group work, always an issue. Like there's the person who's here and does the work, and then the person who's not doing the work, okay? Like I get it. It's like a chronic deal thing. So even though you're working together, each group is responsible for his or her own assignment. You are each going to get a handout, and you are each going to need to turn in your own handout. Do not simply copy work from a teammate. Do your own calculations and compare answers. Okay, so like if you're copying work off a neighbor and they're doing the density calculation, like check their work. Like you do the division, mass divided by volume, and see if you get the same number. And if you don't get the same number, like bring it back to your partner and say, hey, I got a different answer for this. I think we should check our work. Or if you're using a volume formula and you get like one of you is doing the measurements and then you plug it into the formula, do that independently and then compare your answers. Like work together as a team. Now, if you are absent, contact your teammate on the team's channel. So I put you guys into like a little private channel together, like so you can reach out to each other and you can communicate together to see what you missed. Your partner should be able to update you with the raw data. So they should be able to say, hey, I'm working with sample number 4, and here was the mass and here was the volume, and you should be able to do your calculations on your own at home. So being absent does not mean you get a pass on what happened that day, but you do need to reach out to your partner. And if your partner is absent, check Teams to see if your partner is reaching out to you to try to find out what they missed. So be a supportive teammate. You are each going to need to turn in your own handout. So the bottom line is that if somebody is not doing their work, if they're absent and they're not getting the data, then they're not going to have anything to turn in. And that is going to affect their grade. So you're working together, but you are each responsible for what you do. I will hand out the handouts in class, and we'll go over the procedures for the graduated cylinders and the scales and where you should get your materials and put them back and so forth next.